and then we can answer questions in the chat. Okay, so let me share my screen. And can you all see my screen? Okay. I think the first speaker is Max Coleman from Perimeter. Max, please take it away.
Hello, can you hear me?
Yeah.
Okay, so I don't have much time, so I hope we all agree that there's many reasons to consider theories beyond GR, in particular theories in higher dimensions. So it's not very hard to imagine then that the propagation of gravitational waves may differ in those theories, and that the deviations will depend on the distance that the gravitational wave has to travel. So in this third, a few collaborators and myself have been looking at how gravitational waves emitted by massive black hole binary mergers, which we saw yesterday, Lisa will be able to observe, can be used as a tool to constrain the number of space-time dimensions. So why those events in particular? Well, as Kelly said yesterday, these are like standard sirens in the sense that they directly encode the distance to the source. So then if on top of that, you can independently measure the redshift to the source by, for instance, optically identifying the host galaxy, then this provides a unique test of relativity. So the idea is simple. Say we live in a universe with higher dimensions, which are very large, then the waveform emitted and eventually observed by a binary system will be, in this framework at least, damped due to gravitational leakage in the extra dimensions. Then if you further assume that unlike the gravitational waves, the EM waves are only constrained to move in the 4 dimensions, then using a phenomenological approach, you can derive a relation between the EM distance you infer from redshift measurements and the gravitational distance from gravitational waves. And this is the equation you can see on the slide. So of course, when d equals 4, they're basically equal. But then when d is greater than 4, you'll get a systematic overestimate of the distance to your source. Okay, so we have an equation to play with. So we took the massive black hole binary merger catalogs produced by the LISA cosmology working group, basically just massage them into whatever cosmological scenario we wanted to look at. And that's it, we're done. We're plugging this into a Bayesian framework, and then we look at the posterior distributions. So if you look at the few little plots of the marginalized posterior distributions, so this is for like the screening scale and the number of dimensions, assuming that D is 5. So, and then for like different like cosmological scenarios. So here, like you have N1 and N10, where N is the steepness parameter, where it tells you how steep the universe goes from 4D to DD. So what I want you to take away from this is that the number of space-time dimensions, at least in this framework, are quite well constrained, but the screening scale, not as much. And then also, as you would expect, that the more pronounced the deviation from GR, the better LISA is at constraining the parameters. And then the other thing to look at is the other figure on the left, which basically shows the median values of the marginalized posterior distribution for each catalog we looked at for different models. And here, what I want you to notice is that basically the model, so the heavy no delay one, which has the highest number of sources and the lowest error, systematically gives better results, which basically tells us that the ability of LISA to constrain the parameters in this theory will strongly depend on the actual number and redshift distribution of the sources, and obviously the error with which we can observe those sources. But yeah, that's pretty cool, and that's me.
Okay, thank you, Max. So yeah, so our next speaker is Anna Heffner from Guelph, University of Guelph. Anna, please take it away.
Hey, thanks, Juan. Okay, so I'll be talking about regularized self-force towards emeries. So anyone who doesn't know what an emery is, it's an extreme mass ratio in spiral. So you can see that on the right-hand side of my slide. So it's a compact binary where you have one object is about 1 million times more massive than the other. So maybe a stellar mass black hole falling into a 1 million mass black hole. So if I go on to the next slide. Okay, so emeries are pretty cool. I'll just quickly go through this because I only have 4 minutes. They're high precision astronomical probes. The main point here is really that first sentence. So the parameter is measured with variance scale inversely with the number of cycles. So in the last year of an emery, you have 10 to 100,000 cycles. That means you're going to get accuracy of your parameters to 10 to the minus 4, 10 to the minus 5. So things like spin, redshift, mass, you're going to get super highly accurate. Distance and source masses, less so because it's a redshift. And then there's all these other things you can tell if it's an accretion disk, sky location by tracking the constellation of Lisa, and black hole evolution, emery sirens, and of course deviations from GR. So if I go on to my next slide. So basically the whole thing is just that emeries are cool. Okay, oh, stop. Oh no, it's playing. It's okay, so basically what's going on here is basically what we do in the self-force is you perturb the background space-time in the mass ratio. So your background space-time G and then your perturbation H. So you take your Einstein field equations and you perturb the left-hand side. You take your background to be, say, Kerr, and you can throw away that Einstein tensor, and then you just have that perturbation. And then you take the Lorentz gauge, so you get a nice wave equation. Okay, and then if you take the next few clicks, okay, so you take the only mass of the system to be your little guy, and that gives your stress energy tensor. And then the next, I shouldn't have done so many builds. And then the next clicks, there should be something else. Yeah. And then you can just use the conservation of stress energy to get your equations of motion. And what it turns out is that your acceleration in your at zero order is just a geodesic of the background space time. And then at first order, you get a deviation. So you kind of think of, because of the presence of a small black hole, it's imposing a force on its own motion. And that's why we call it the self-force. Okay, next slide is regularization. I don't think I have time for this. You can just kind of click all this away, because I was way too optimistic about time management, which is an ongoing problem. Okay, so basically I'll just jump to about some regularization. So the whole idea about this is, maybe what you noticed when we looked at the stress energy tensor is that we do actually assume that the little guy is a point particle. Okay, which is not very realistic, and that introduces a singularity that you have to deal with when you're actually trying to numerically solve the wave equation. So what we have to do is, because we've made this assumption of a point particle, we have to remove the singularity. And the previous slide was telling you how we actually model that singularity, but basically what you do is you try to get a singularity that completely captures the singular behavior, but doesn't remove any effects of the movement or the acceleration that's imposed. So basically, one of the ways of doing this is a mode sum regularization. So you literally just calculate your singular field and you subtract it mode by mode from the retarded field that you actually calculate numerically. So if you hit the next button, okay, and basically what this means is as you go up in L's, if you get the singular field to a certain order, you get a higher convergence in L. So you need less, you have to calculate less modes to get the same accuracy. And so what I've shown here is F theta for the scalar case. And if you can hit one more click to get this red line up. So basically, if you look at the blue dots, what's happening here is if you get the first two orders of your singular field, you can see that how you're getting to higher and higher accuracy, you're going downwards. The new parameter, which is D, gives you that yellow line. And that basically means if I want something to 10 to the 6th order, if I go across this red line, I only need, I don't know, 12 or 13 Ls. But if I want to do it without, well, by following the blue line, I'm going to need maybe 20 or 25 Ls. And those Ls are super highly computationally expensive. So having the higher parameters is a really big deal. And this is F theta. So this is for a generic inclined Kerr. So again, to put that in perspective, those blue dots were first calculated in 2001 by Barak. And it's basically taken us 20 years to get these yellow dots. And I'll end there. Thanks.
Okay, thank you, Anna. Our next speaker is Zhen Pan from Perimeter. Please take it away.
Okay, wet emeries may be more common for spaceborne gravitational wave detection. Okay, I will explain what are wet emeries and what are dry emeries next. Here are the pictures for the two different kinds of emeries formation. On the left, you will see a massive black hole in the center and the stars and the stellar massive black holes around it. So we consider one of the stellar massive black holes around in the massive black hole. So for each orbit, there will be some gravitational wave emission from the stellar massive black hole. If the gravitational wave emission is the dominant process, then the orbit will shrink continually and form a stable emery. So we call emeries formation in this channel as dry amorphs. On the right, the setup is basically similar, except the massive black hole is accreting. You will see there is the accretion disks. So the stellar mass black hole will be first captured to the accretion disk due to the density waves generation. After the stellar mass black hole is captured to the disk, it will continually migrate inward until to the vicinity of the massive black hole and form a wet amory. Next. So we did some calculation for these two formation channels. In this plot, the x-axis is the massive black hole mass, roughly from 10 to the 5 to 10 to the 7 solar mass. The y-axis is the amory formation rate per AGN for the wet channel, and the formation rate per massive black hole for the dry channel. You will see the lower three lines as a formation rate for the dry channel, and the upper four lines are different models for the formation rate of wet amories. You will see the two are different by a factor of from 10 to 1,000. Next. But not every massive black hole is accreting. From the local universe, the AGN fraction is about 10%. For higher redshift, the AGN fraction will maybe higher, about 10%. If we take the most conservative fraction, 1%, we can calculate the wet amory formation rate versus the dry amory formation rate per year per cubic giga per second. We see the wet formation channel is roughly 10 times higher than the dry formation channel rate. Next. And the amories from the two channels have very different source properties. For example, the wet amories usually have a very low eccentricity, and the inclination angle will be roughly 0 with respect to the massive black holes being equatorial plane. Also, the accretion disk will induce some detectable phase shift to the amory waveform. So from all this difference, we can distinguish the two channels. Thank you.
Okay, thank you, Jen. Our next speaker is Davide Recco from Perimeter. Davide, please take it away.
Thank you. I would like to thank the organizers for giving me the opportunity to talk about my work here. And I want to talk about cosmological gravity wave backgrounds, fleshing out two different scenarios I've been working on. One is primordial black holes and phase transitions. So next slide. Primordial black holes are black holes that would have originated not from the last stages of stellar evolution, but from the collapse of large overdensities in the early universe. And they could even constitute dark matter. And there have been many studies looking at possible signatures or constraints on the parameter space. And as you see in this plot, where the horizontal axis is the mass of the black hole, and on the vertical axis, you have the fraction that could constitute dark matter. You see that the constraints are cutting the possibility that PBH can be the totality of dark matter, apart from a range between evaporation constraints and optical lensing constraints. As you see next slide, this range could be potentially covered by future X-ray lensing observations, but the prospects for these are quite uncertain. But actually, LISA comes to rescue in this case. Next slide. Because the collapse of large overdensities not only originates the primordial black holes, but also a background of gravity waves. And if one checks the correspondence between the frequency of the gravity waves and the mass of the PBH that would have originated, you see that the green box translates in the gravity wave space precisely in the range of frequencies that LISA can detect more confidently. And so LISA will ultimately test this window as an option for PBH to be 100% of dark matter. Then next slide. I would like to mention another topic that is the possibility of detecting a phase transition that would be the transition of for some scalar field from a given expectation value in the false vacuum to its true vacuum. And this, in first order phase transitions, happens with the generation of bubbles inside which the field is in its true vacuum. And these bubbles expand and eventually engulf the whole universe. And when the bubbles collide, and from the interaction with the plasma, a background of gravity waves is generated. This background is generated locally. In each Hubble patch, the physics is generating these gravity waves, and different Hubble patches are uncorrelated by causality. And so this information, plus the fact that phase transitions are fast in time, constrains the tilt of the gravity wave spectrum at low frequencies to be the same regardless of the model generating the phase transition or whatever is the mechanism to generate these gravity waves when they are causality limited. And this tilt is 3. So you see in the plot on the right, the universal scaling as f cube at low frequencies, regardless of the parameters of the model. And so we see in the next slide, we have been studying what we can learn from this background. If we happen to detect such a background from a phase transition, we can look at the low frequency tail. If we manage to observe it with high enough precision, we can learn a lot about the physics of the early universe, not of the details of the model that generated it, but details about the content of the universe and the cosmological history. In particular, we have been looking at the possibility of detecting free streaming particles, which are weakly coupled relativistic particles like neutrinos, but extra neutrinos. And the tilt at low frequencies directly relates to the abundance of these particles. And we could measure them possibly in a complementary way to delta N effective measurements. And then we can also study what is the impact of alternative cosmological histories to the spectrum of a gravity wave background. And in particular, a matter-dominated phase, if it happens after the generation of the gravity waves, can boost the spectrum of gravity waves at low frequencies, thus making them even more observable for a detector. Thank you very much for the attention.
Okay, thank you, Davide. Our next speaker is Vasyl Todorinov from University of Lethbridge. Please take it away.
Hello, everyone. Today I'm going to talk to you about quantum gravity effects on gravity wave detection. Can I have the next slide? So we have first, what is quantum gravity and why do we need it? We have 2 theories that describe nearly every phenomenon in the universe, right? This is general relativity and quantum mechanics. However, they don't play well together due to fundamental differences in their conceptions. General relativity is classical and it's deterministic, while quantum mechanics is probabilistic. So they clash on this fundamental level. Can I have the next slide? This is where theories of quantum gravity come in. These are theories, a family of theories which have different approaches and methodology to tackle the problem of quantizing gravity itself. Most prevalent members of the family are string theory and loop quantum gravity. My personal expertise is in the generalized uncertainty principle, which is a phenomenological model of deformed position momentum commutator. All these theories have something in common, and that is that none of them have experimental confirmation or support yet. Can I have the next slide? This is where LISA comes in. It will open a new window to the universe, allowing us to detect compact like gravity waves from compact objects captured by supermassive black holes, like the few talks before mentioned. Compact binaries in our galaxy, binary supermassive black holes, and the quantum fluctuation in the universe itself. So how do we expect gravitational wave detection to be affected by theories of quantum gravity? Can I have the next slide? First, we can focus on the detector itself. A study from Dr. Bosso et al. Has shown that if we use squeeze states, there will be quantum gravity phenomenon encoded into the shot noise of the detectors itself. These are the quantum gravity corrections that we expect to observe. Furthermore, we recently were able to find a quantum gravity modification to the Einstein tensor, which you can see on the bottom equation, which will affect the frequency of the quasi-normal modes that we expect to detect coming from gravitational wave sources. So now we have this quantum gravity encoded into the frequency of the wave we detect and via the way the waves are generated. Can I have the next slide? More on this. The quantum gravity predicts also a modification to the propagator of the gravitational waves themselves, which will affect, which will be encoded in this ratio between the gravitational wave luminosity distance and the electromagnetic wave luminosity distance in the red delta function of z prime, delta of z prime. This is not a delta function; it's a function which will contain this quantum gravity phenomenon in itself. Finally, a work which is a little bit more in its early stages, we expect quantum gravity relics to be encoded into the primordial gravitational wave power spectrum, as the talk before me mentioned. Next slide, please. Finally, I want to say that I'm very excited of the new physics that LISA will potentially detect as the most accurate test of general relativity devised so far. And thanks for the attention and for the organizers to providing me with this opportunity.
Okay, thank you all the speakers. Let me stop sharing for now and see if there is any questions.